All right, welcome to day 1 of 2 as we prep for exams. Just a moment ago, I had emailed you out the slide deck for this. So if you like to follow along on the slides, some people like to open it up as a PDF and mark on it as you go. You can do that as well. I will not get through all the slides on this deck, the 28 slides today, I doubt, just because of the time it's going to take to go through them. So then when the other ones we finish up the next time we get together. So before content, just some reminders that I've said multiple times. Here it is in writing as well. Don't forget that on test day you arrive here by the test start time. No admittance after the test begins. That way it doesn't interrupt those that are already beginning and working on their exams. Make sure your laptop or tablet is charged, or bring yourself your own extension cord so that way you can reach to wherever your desk is. Make sure you have a calculator. No phones, no watches are permitted. Your laptop probably has one on there too. You can probably just pull that up. You can have up to one full standard 8.5 by 11 sheet of paper with front, back, anything you want. Example problems, flow chart, scripture references, words of encouragement. You name it, you can have it written on there. It'll get turned in with the exam. And then the day before the exam, I will email you the data sets so that when you are doing a problem, if it requires data to be entered, you don't have to be then manually entering it. You can just copy and paste it. Makes it a lot simpler. So, before we get to actually working problems, I'm going to spend a quick time reviewing. So take 2 minutes, think, and turn to the person next to you. What are the key characteristics of a designed experiment and observational study? Go. All right, that was your 2 minutes. So a designed experiment, I heard some of these words out there. This is the only way to prove causation. We've been doing a bunch of hypothesis tests. Remember, a hypothesis test does not prove causation. It proves whether a claim is true. And a hypothesis test is often used when doing when doing a designed experiment. You usually end up with a hypothesis test at the end to then find out, did what I think was going to happen actually prove cause and effect? So a designed experiment also has key aspects: randomization, replication, control. Those are the 3 key words. People are randomly assigned to a treatment, or the treatment is randomly assigned to them. Or even if you take a group of volunteers, and you can actually, in bigger cities be parts of, studies, medical tests, if you qualify, where they give you certain things. So you are a volunteer, however, they still randomly assign you into either a treatment group or a placebo group. And then control is the part where the recipient cannot know what they're getting for a treatment. When we're talking about people. Lab rats, of course, they can't think, and it doesn't matter if you tell them that you're giving them a tumor or not a tumor, or giving them some medication or not a medication. They don't know one difference from another. So randomization, replication, control. And then observational study, I heard the words out there: correlation. You can also say association. It's basically, hey, there's something going on. And really what makes one of these, it's either you're missing, any one of the components of a designed experiment, and it now becomes an observational study. So if you're polling people and asking their opinions, observational study, because there is no treatment group, right? So that treatment would fall under control. Observational study, I take a look at everybody in this classroom, and we look at a relationship between your GPA and your height, or something that wouldn't make sense. It's an observational study because there wasn't randomization, because I'm just selecting you. Also, there's no treatment. I cannot change suddenly your height to see if that affects your GPA, and vice versa. There we go. Sampling methods take about 1 minute. Try to jot down all that you remember for the different types of sampling methods. Go. Oh, and discuss with your neighbor if you're like, I can't even think of one. Get your brain going. Or they go, well, there's this. You go, oh, that's right. and then jot down as many as you can. Quick, go. All right. The granddaddy of them all, the best way to ever do any type of sampling is simple random sample. Simple, the word that means that everybody has an equally likely chance of being selected. And then random, there's a randomization process by which you then sample, simple random sample. I heard words like stratified. When you think of stratified, you think of strata, either in thinking similar to like the Earth's crusts and the different strata there, or also as you go up in the atmosphere, you have different layers. Those are different strata. It's a hierarchy, stratified sampling. I could do stratification, stratified sample proportional allocation. What that would be, proportional means in proportion. So if I looked at all freshmen, sophomores, juniors, seniors at Simpson, and then I randomly selected a 2% of each of those grade levels, or statuses, that would be proportional, and allocation, stratification would be freshman, sophomore, junior, senior, because there's an implied hierarchy there. Cluster. Who's got a good explanation of cluster sampling?
Divide participants into clusters, randomly select clusters.
Nope. You cannot create clusters. They exist already. So you can't assign them to clusters. Now, if our book says that, our book is misspeaking, but a cluster sample is where you have various types of groups of people who are together for some reason. They make a cluster. And you can only be a member of one cluster. And then you go to a cluster, and then typically you sample everybody in that cluster. So if I were to go to think of all the classes that are happening right now on campus, and I randomly select 2 of those classes, I would then go to those classes and then sample everybody in each of those 2 classes. So there will be some commonalities for those individuals because they exist in those clusters. So that's cluster sampling. We have convenience sampling, right? Talking to whoever shows up at the cafeteria and talking to them about whatever your question is. That's convenience. You could add a layer to that and have like a convenience systematic sample where you go stand at the entrance to the caf and every 5th person you talk to. So systematic is there's a system to it. Every 3rd, every 5th, every 100th, whatever it is. Am I missing any? Yep, sample method. So then probability. Ideas in probability that we talked about in the past. Independence is one. And independence from a mathematical point of view is if I have the probability of A, if that equals the same as the probability of A given B, which means if I know B happened, what's the likelihood that A happens? If that's the same as just A happening, they're called independent. Independent because knowing the outcome of B didn't change the probability of A. You could talk about things like probability of a heart in a deck of cards is 13 out of 52. Probability of a heart given that they're aces. All right, well, there's 4 aces. One of them is a heart. Both are 1/4. That means the events drawing a heart and drawing an ace are independent events. Mutually exclusive are 2 events that cannot happen. In a Venn diagram, if this is group A and this is group B, mutually exclusive means there's no overlap. You cannot be in both at the same time. Intersection, C. So now if we're talking right here, that event is A intersect C. And then that's where we do a lot of our probabilities. If I do probability of that happening, that's going to be the probability of A times the probability of C given that A just happened. Union would be all of B and all of C, and would be represented as B union C. And if we're going to do probability of that, that will be equal to the probability of B plus the probability of C And like we did when we were talking not too long ago, if I count all of this once and then all of this, that middle section right there, between C and B where they intersect, I've actually counted that one twice, which means I'll have to then subtract away one of that. So one of the intersections has to be subtracted away because it was counted twice. And then from there, we launched in and spent a considerable amount of time on the binomial because it is a specific type of probability scenario. Two outcomes only. Every outcome is independent of every other previous outcome. The probability of success is a constant, and there's a finite set of trials. So when thinking about what makes it a binomial, it's identifying all four of those. All right. And then the formula was, if I have probability that x equals r, NCR times P, which is probability of success, to the R times Q to the N minus R. And Q is 1 minus P. Mean, median, mode. 1 minute, turn and talk, go. So again, when you're doing it, make sure that when you make a statement, you add quantifiable values that go with it. A distribution versus a sampling distribution. A distribution is if I have some type of context, IQ scores, which we know the test itself is designed to be normally distributed. SAT, if you actually took that, most people don't anymore, although I think it's coming back. Ivy League schools have started doing it, which means there's going to be a trickle-down effect. But those tests are designed to be normally distributed when they get the scores. A lot goes into designing a test to be like that. So IQ test, all right, that's a distribution. If I look at things like, I'll erase SAT here for a second. If I look at household income, okay, you wouldn't necessarily know this, but I do. It is very right skewed. All right. And when you talk about middle class, people don't actually do this, but if I look at the middle 50%, that's a 5-0, that would be considered your middle class. And this upper limit is somewhere in it's like right around like 36,000. And you might say, wow, that is not very much money. That's because there are a lot of families that do not make a lot of money. Yeah. And if you're at college, you probably, not always, are coming from a group that's out here. But not always. All right. If I talk about sampling distribution, then it's like saying, well, if I take one data point, another data point, a third data point, a fourth data point, a fifth data point, and I average those up and I plot it, it's going to be right here. And that's going to be 1 X bar. Now, I'm going to repeat that 10,000 times. And all of the dots here will be normally distributed. Over here, I had a normal curve. The mean was mu. The standard deviation was sigma. This distribution of IQ scores, where it's the average of 5 people randomly selected, will be a normal curve. We'll have the same mean, 100, because that's what it was over here, I said. And the standard deviation will be sigma over the square root of n, known as our sampling standard deviation. Distribution, sampling distribution. The sampling distribution will always be narrower than the original distribution because my spread is going to be divided by a number that's greater than 1. Right there. And way back in the machine early in the semester, we did this website where if this was my original population of values, and if I sampled 2 items and found the mean and then repeated this 10,000 times, the sampling distribution here is still a little right skewed. But also we notice it's narrower, right? See, these are scaled the same, 0 to 32. That goes out there. When I sample sizes of 10, and I'm doing the mean, now my distribution's looking pretty close to normal. And this is how we developed the idea of the central limit theorem, which says as my sample size increases, my sampling distribution approaches a normal curve. And we actually find through a very rigorous proof that we didn't do in class that n is 30. Once n is at least 30, sampling distribution is going to be approximately normal. From there, we rolled into confidence intervals. But what's the purpose of a confidence interval? Why do it at all? Think for a moment. If you want to bounce an idea off a partner or neighbor, you can do that. All right, what is the purpose of a confidence interval? Go ahead, anybody just shout it out. Don't be afraid. Yeah.
The true mean or whatever you're trying to look for of the sample, the true and the
Yep. We're looking for we want to find the true mean. We want to find the mean of the entire data set. Because most things that exist out there that you're going to study, you're going to go do as a career, you're going to look at and contemplate and wonder, I wonder what the average fish size is in this lake. You can't take every fish out of that lake to find that out. So you have to do random sampling. All right? Take random sample of fish, and probably not going to be doing it by catching fish either because they're going to be a different type of fish than other fish. So they go out in a boat with electrodes, and they fire it away, and they stun the fish, and they float to the surface. They quick take them out, measure them, put them back in. The fish live. But then they're going to start getting an estimate of numbers of fish or size of fish or things like that. But if I only have one point, that doesn't do me a lot of good. So instead I make an interval. X plus a critical value times the standard error. And this point down here is X bar minus that same critical value times the standard error. If it's one sample, it's S over the square root of n. If we're talking about a proportion, confidence interval it becomes a p hat. And then for that, the standard error is PQ over n, and the square root of the whole thing. And critical value is going to be Z or T. And although we didn't do it, you can do confidence intervals in chi-squared and in F. We didn't, we won't, it won't be a question on the exam. But then I've got a bigger, wider net to capture that true mean. How do I make a bigger interval? Well, I can have a smaller critical value, which means if I'm less confident I'll have a smaller interval. If I want to be more confident, I need a bigger interval. If I have a larger n in the denominator, that makes this number smaller. Well, that means the interval gets narrower. These are hard to see, so I'm going to zoom in on them. On this one, sample sizes of size 10. So the original population had a mean of 50, standard deviation of 10. I could select that it was a normal distribution. I did this how many times? 100 times, it looks like. Intervals 1 to 100. What you see in here, the red ones, just in random sampling, I happen to get one interval that I created that does not capture the true mean. The true mean we said was 50. And actually in here, we ended up with 7 of them did not include the true mean. All right. So in random processes, it's still possible. If you were to repeat the process 100 times, you would expect there to be 5 of them that would not include the mean because it's a 95% confidence interval. But we don't know. You're again, when this is really happening out there in the quote, the real world, you're going to sample one and you're going to get this interval right here, and you're just going to have to hope that it included the actual true mean. Some people say, well, couldn't I just do another interval? Then if they both overlap, then that overlap would be maybe, but not always. So that's samples of size 10. This is samples of size 30. What happened in those intervals? How are those intervals different? Yep, the endpoints became tighter. They're narrower intervals. This one interval at the top, if I just look at that one interval, it's narrower than the one that was over here. Why? I sampled more. So I have s over square root of 30 instead of s over the square root of 10. Dividing by 30 reduces my standard error, which impacts the confidence interval width. And then finally I did samples of size 100. And you can see they get narrower yet. Changing sample size does not change my confidence level, just the interval width. Because some people say, well, if I just sample more, I'll have more confidence, which is not accurate. You'd have a narrower confidence interval. Now, if you wanted to go back and have then sample 100, but have an interval this wide, then that would mean I'd have a higher confidence level. Here's a phrase. This is grammatically correct. Aside from that, when people are like, well, first we're going to fix your grammar, Mr. Stefan. No, my grammar is correct. When you're talking about data versus datum, singular, plural, that kind of thing. Anyways, when you read this phrase, do the data provides, you need to then think, I am going to do a hypothesis test. Is there sufficient evidence to prove? Another way of saying, I'm going to do a hypothesis test. And the minute that happens, you're thinking, what are all the things I have to include in a hypothesis test? Take 1 minute, turn and talk with the person next to you about what the core elements are that are required every time you do a hypothesis test. Go. All right, there we go. What are they? What is required every time you do a hypothesis test? Give me one. Conditions. You need to identify the conditions because that determines what type of a hypothesis test you're going to do. T, Z, proportion, chi-squared homogeneity, chi-squared independence, chi-squared for the variance, F-test with a one-way ANOVA, or F-test for the variance. So first thing first, you got to go through all your conditions. What else do we have to have?
Type 1 or type 2 error.
That'll be at my end when we talk about error analysis. Which we'll be talking about whether it's a type 1 or a type 2 error. Or what they would be in context. Think of the flow of the problems. After you figured out which tests you were going to do, what did you have to start with? Hypotheses. So you got to write down your null hypothesis and your alternative hypothesis. And depending on the context will depend on, will this be a mu? Will it be a p for population proportion? Will it be beta? Beta would be for the slope in a least squared regression line. Will it be variance if we're doing a test on a variance? Whatever my population value is, and they except for p. Now, there are some traditionalists out there who would say, well, yes, we do use the Greek letter capital pi, not to be confused with lowercase pi, to mean the population proportion. I stick with just the letter p. And then your alternative will be either greater than, less than, or not equal to. And that determines whether it's one-tailed or two-tailed. Then what? Got to show the formula. Then some calculations. Now, granted, the calculations we're doing are almost all done online somewhere. So the difference from the formula to the calculations is the formula just has the regular formula. The calculations then has the values that you put in for those specific things. So if I'm doing the test on the variance, I'm doing, and that would be for one sample, a chi-squared test on the variance. And that would be n minus 1 s squared over sigma squared. And then I'd use that in a chi-squared distribution, df equals n minus 1. All right. After I have my calculations, I'm going to make a conclusion. Either I reject the null or I do not reject the null. 6, interpretation. And then 7, where asked, error analysis. What would a type 1 error be? Or really what it would come down to is you make your conclusion. If your conclusion is I do not reject the null. If you made an error, then that would have been wrong, and that would have been a type 2 error where I did not reject the null when I should have. If my conclusion is reject the null, and I later on find out I was wrong, that's a type 1 error. I rejected the null when I shouldn't have. So then, with that in mind, a random survey of 75 death row inmates, so my N is 75, revealed that the mean, so I'm going to do a test about the mean, which eliminates a lot of the other things, right? Chi-squared and F-test are off the table. It's going to be either Z or T. For the length of time on death row is this. So my null hypothesis is that the average is 17.4. And a standard deviation of, this is my, no, take that back. This was my sample value. Because down here, that's the 16. But my X bar is 17.4. My S is 6.3. Those are the values that they give you in the equation, in the context of the question. But I've not done the conditions. So the conditions would be 1. Is this a random sample? Yes. So for my conditions, S, is it a simple random sample? Yes, it is, because it indicates there right there. Independence. Does one death row inmate's sentence impact another death row inmate's sentence? Since they do not, they're independent. I'll be writing that out in words. Normality. Do I know that the population of death row inmate sentences is normal? No, it does not say that. However, since n is greater than 30, it's 75, n is greater than 30, that means the sampling distribution of inmates' length of time is going to be normally distributed. I do not know sigma. Therefore, I am using T procedure. So I'm going to write my formula. T equals x bar minus mu all over s over the square root of n. T equals 17.4 minus 16 all over 6.3 over the square root of 75. And we want to determine if the population mean time in death row will be more than. Draw my picture. Greater than means I'm top, this is where I'm shading. And whatever the T value is from here, my degrees of freedom will be 74, which is n minus 1. There's n. N minus 1 is 74. I would use the applets page for the T distribution, put in 74 degrees of freedom, and then whatever this number is to get my P value. So in calculating this number here, for the T, we said was 1.9245. And on the T applet, 74 degrees of freedom, it says that this area of the upper tail, because you got to choose the correct drop-down menu, 0.02907. I will reject the null and accept the alternative hypothesis. There is sufficient evidence to show that the average length of time on death row is more than 16 years because our results should have only happened 2.9% of the time if the null was true. Since this is so uncommon, I am rejecting the null and accepting the alternative. $511 homes, earthquake preparedness recommendations, whether or not they meet. So either they meet or they don't. So that means this is a binomial situation in terms of there's only one or two possible outcomes. So they meet, so that's going to be P. They don't meet, that's Q. I need to create a 98% confidence interval, which means P hat plus or minus Z times square root of PQ over N. Do I know P or Q, the actual population values? I do not. It's not told up here anywhere what the actual proportion is. I did a random sample. All right, so let me do that too. Conditions. Do conditions on confidence intervals too. It is random as noted. Right there. There are over 5 successes and 5 failures. Therefore, use Z for proportions. 98%. If you do not know 98% off the top of your head, back to the applets page. So go back to the applets page. Scroll down until you find normal. You'll click on normal. And then in the red box, or salmon colored box, whatever you want to call that color, you need to put in a percentage, and then it'll tell you the corresponding z-score. So 98% confident means 0.01 at the ends. So again, thinking about a normal curve. If this is 98%, this is 1%, which is 0.01. So if I do that in the normal applet, I get, and I'm going to start plugging in numbers into my formula now. P hat will be 279 homes out of the 511 plus or minus 2.326. And that number came from the applet where I put it in mine. I put in 0.01 and I had greater than, so it gave me this little tail area. That will be my 98% confidence interval Z value. Times, and here's the tricky part in confidence intervals with proportions. People often think, well, I will just use P hat, and that would not be accurate. If I have no idea about what P and Q are, I take the most conservative, aka the least telling response, which is 50-50. If I really have no idea, then worst case, it's 50-50. So my P will be 0.5. And then 1 minus P, which is Q, is also 0.5. And then divided by 511. Because that's how many I sampled. Plugging those in, punching your calculator keys, ta-da, it gives you a result. After you get the result, then you would say, I am 98% confident the actual proportion of homes, is it meet minimum? There we go. That meet minimum earthquake standards is between the bottom number and then the top number for whatever you get in that confidence interval. All right. And because it's a proportion, you can change it to a percent. You could, I'm 98%, but what you cannot say is I'm 98% confident that between 50% and 58% or whatever they are meet standards. You're not saying how many homes do, you're saying I am confident that the actual proportion is somewhere in this range. But again, I'm not going to calculate this out right now because honestly, the numbers are not the most important part. Conditions, correct formula, knowing what goes into the formula, and then communicating interpreting the results. That's where our significance is going to need to be spent, is being able to do this well. We'll pick up then with this. A student at a four-year college claims that mean enrollment. So the moment they say that, mean, checking into that and being like, all right, so I'm going to be testing for mu. Mean enrollment at four-year colleges is higher. There's going to be a greater than symbol somewhere than the two-year colleges. So I'm actually going to be comparing two means. I'm going to have a mean for 4-year, so mu sub 4. And then this will be a mu sub 2 for the mean of two-year colleges. And we're going to say null hypothesis. I haven't done any conditions. I don't know what test I'm running, but I recognize this is going to be a hypothesis test. So I want to write down, what are my hypotheses? My first one will be that mu4 is equal to mu2. Another way to write that is mu4 minus mu2 equals 0. Because if they're the same, and I subtract them from each other, they'll equal 0. All right. My alternative is that they suspect that enrollment at four-year colleges is higher than two-year. Mu sub 4 greater than mu sub 2. Or another way to write that is mu sub 4 minus mu sub 2 greater than 0. So now that I know it's greater than 0, I'm actually going to sketch my picture over here quick. Assuming I'm going to get to normal. So again, I'm assuming something right now. I'm going to actually have to go back and verify. But if we can assume that the sampling distribution of those averages is normal, so if x bar 4 minus x bar 2, if they follow a normal curve, centered at 0 because we said that the difference is 0, we are testing for greater than, which means I am testing for this tail up here. It's going to be a one-tailed test because it's greater than. And greater than being the upper end, or the less formal way of saying it, which way does that point? It points to the right, so I'm going to do a right tail. All right, so now my conditions. Were these random samples? It says 2 surveys are conducted, randomly surveyed, stated as such. Are they independent? Yes. Four-year college enrollment does not affect two-year. Normality. Let's see. We had a sample size of 40 for two-year colleges, and we had, and 41 of the four-year. Since both samples are over 30, the sampling distribution is normal. And then the last condition is, do I know sigma? Do they tell me anywhere in the problem what the population standard deviation is for those two samples? It tells me the mean enrollment and the standard deviation of the sample, but that is not population. So sigma is unknown. Use T distribution or T procedure, and technically it's going to be a two sample. It's a two sample T procedure. Then it's looking at, after going through that, so far much of this has just been looking at your flow chart, remembering how to write hypotheses, how to verify normality of a sampling distribution. And then it's the, well, what formula do I use when it is a, come on, it's not what I wanted. I want to select everything. It won't let me select everything. There we go. I'm going to shrink it just a little bit. Once I know all of those numbers are in there for the T, that would then be time to put that into a calculator and figure out what that is. And I have a calculator, someone else should have a calculator. Verify my calculations as we go through it. So the numerator is going to be 398. And I'll do a whole bunch of stuff in the denominator. 81, 91 squared divided by 41 plus 4777 squared divided by 40 is that. So I have a very large number in the denominator, but I take the square root of it. Square root of the answer is 1666.5. 398 divided by that is a t-score of 0.2388. That's not a very big t-score. So then if you would go to the applet page for the t-distribution, applets down to t. I'm doing it on my laptop, that's why you don't see it on the screen. If I do degrees of freedom 70, what did I say, 79, and a t-score of 0.2388, it gives me this area up here is 0.4059. That's huge. Very, very large one. Now, this assumes that I entered this into my calculator correctly and I got the answer, and if someone else got the same answer, they're going to bobblehead a yes. I'm getting a no. What number did you get?
0.2679.
Okay, could just be a rounding error. 0.2388, 0.2679. If all these numbers are in here, that was probably just a rounding error. Which means this number is very large, greater than 5%. My conclusion, I do not reject the null. There is not enough evidence to suggest that four-year college universities' enrollment is greater than two-year colleges. What we saw could have happened 40.6% of the time, which is really, really not unusual. I would call that common. So if you're kind of wondering how things get mapped out in terms of if this is a 4-point question, like all of them are, 4 is essentially correct, 3 is substantial, 2 is developing, 1 is minimal. So minimal would be, you've got your hypotheses, you've got conditions, and whether the conditions are right or wrong, you have the right formula to go with the conditions. That's going to get you a 1. Developing would be kind of all of that, plus you know that that's the right formula, but maybe then you do something completely wrong down here, or, yeah, pretty much from there on down, there's nothing here. A substantial would be this. Even if this is wrong, you have a formula that matches your conditions. You run through the conditions all the right way. You get a value. You interpret you give a conclusion, and you interpret the results in context. You can get a 3. So even again, if you use the wrong formula with the wrong conditions, you can still get a substantially correct, because the only thing you did wrong is you just chose the wrong technique. But you know how to set it up. You have a picture. You got a formula. You put in numbers. You got a conclusion. You told me whether or not you reject the null or you don't reject the null. And then you wrote a great interpretation in context. That, to me, because communication is such a big thing. All right? If you get to a place like this and you're like, I just don't even know where to start, but I know it's a hypothesis test, you can make an arbitrary t-value, but first thing you'd have to look at is say, well, 4777, the means, 5068 is less than technically 5466. So the t-score will be positive because it'll be this one minus this one. So if you give me a t-score of some number, and then you explain where you did on the applet to get an actual proportion, even if you're like, I don't even know what I'm doing, didn't pick the right formula, but say t equals 1.21 and 79 degrees of freedom, I'm going to reject the null, and then write an interpretation about that. If you would have that, so just an arbitrary number that you picked, but recognizing it was positive, degrees of freedom, conclusion, interpretation, and a hypothesis, you'd probably get a 2. And that's a developing. Because that means you're on the right track. You maybe couldn't remember the conditions, got lost up in some of the details, lost track of the formulas, something there, but you're understanding what's going on and what it's going to imply and mean when we're all said and done, you can still get there. Back on that last one. But even if you did that, say, and you got a 2, but then down here, instead of saying something, you said, I accept the null, well, then it goes down to a 0. Because you never, ever, ever accept the null. Ever. All right. Oh. All right. This will require stat blue, so have that open so you can be practicing where to put things in. Online stat suite. Okay. So one of the questions in a study of marital satisfaction of dual career couples was to rate the statement, I'm pleased with the way we divide the responsibilities of childcare. So it assumes they have children. All right. The table contains 10 of the paired responses. That's an important word. For husbands and wives. Conduct a hypothesis test to see if the mean difference of husbands versus wives' satisfactions level is negative. So they're asking, is the difference negative? Meaning that within the partnership, the husband is happier than the wife. So if it's negative and the husband is happier than the wife, the difference column would be wife minus husband. All right. If you did husband minus wife, ran through the whole scenario and did a hypothesis test, you could still get a 3. But you'd have to recognize that the difference that they're talking about is like, oh, when they say it's negative, meaning the husband is happier, and isn't the higher number happier? Or is the lower number happier? One, strongly agree. So 1 is really happy, 5 is very unhappy. So wife here, 2 minus 2, 2 minus 2, 3 minus 1 is negative 2. So I put in the differences for you. At this point, even though it looks like it's a 2 sample, it's not, because they're paired. We want to look at every husband-wife pair as a single data point. So that means this is my data set that I'm going to do a 1 sample test for. My null hypothesis will be the average differences is 0. My alternative hypothesis is the average differences is negative, less than 0. Is one couple's response independent of any other couple's response? Yes, independence. Were my couples randomly selected? It doesn't say. I'm going to have to assume that they were randomly selected, and I would say, I have to assume they were randomly selected. It does not say. Normality, we don't know. My sample size is 10. And that's less than 15, so I'd have to make sure there are no outliers. So how I do that in Stat Blue, grab the normal probability plot on the right, put in your numbers, calculate. My normal probability plot looks like this. Something like that. It's not great. So I would have to identify and say something along the lines of the NPP, that. And if you do a normal probability plot and refer to a normal probability plot, you quick sketch or normal probability plot, does not appear very linear. But R equals 0.65. So we will proceed anyway. T equals x bar minus mu sub d over s sub d over the square root of n. I go back to StatBlue and I do a one sample t-test with my differences, 0, 0, -2, 0, -2, -1, 0, 0, 0, 0. Calculate. Oh, I did a confidence interval. Dang it, did the wrong one. Copy that. Go back to home. One sample t hypothesis test. There we go. Put it in there. Difference is 0. I'm sampling for less than. And I calculate. The husband is happier than the wife. Put that on my next slide. Yes, I did. So there's the numbers are in. Enter this number as 0. We're saying the difference of them is 0. It's the same. The difference is, right? Negative, so less than 0. 5%. I can check my context. Sure. It gives me this. T. We're doing less than. My p-value here, 0.0479. Since 0.0479 is less than 0.05, we will reject the null. Here we go. One. Since our results would only happen 4.8% of the time by chance, there is significant evidence to show that the husband perceives their happiness level as better than the wife does. And if you look at, like at the inside of StatBlue, it does give you an interpretation, and it said in green, assuming that the mean mu is 0, that is the differences is 0, the probability of seeing a test statistic of negative 1.8605 is smaller than 0.0479. That's really not an interpretation. That's an explanation. An interpretation is telling what that means in context of the question. It also doesn't say, well, it does say below that in blue, reject the null, because p.0479 is less than 0.05. And the 0.05 is a default. It can be changed in StatBlue in that drop-down menu. You can change it to whatever you want. It typically, we just leave it at 0.05. Now, I need to switch to my other device. So it's projecting LR204. There we go. New question. Research conducted a study to find if there's a difference in the use of e-readers at different age groups. Randomly selected participants were divided into two age groups. In the 16 to 29 year group, 7% of those surveyed use e-readers, while 8% of the other participants and older use e-readers. So you're thinking, like, did they ask a question? We need to conduct a study to find if there is a difference. Null hypothesis is that the proportion of young is equal to the proportion of old, or something like that, so we can see what it is. My alternative hypothesis is determining, is there a difference. Two sample proportion test. Being in random sample, randomly selected, so I'd indicate random as indicated. Independent, being in one group, or one person in one group does not affect someone else's response as to whether or not they use an e-reader, so independent. Normality, there are over 5 successes and failures for each. How do I know? 7% of 628 is over 5. Okay, 11% of 2,309 also over 5. So since there are over 5 successes and 5 failures for both, the sampling distribution is approximately normal. No, I did not write all that down, but you would on the space provided on an exam. But I just determined normality. I'm going to go like this. Zero's in the middle. Proportion test is Z. So then I'm going to go to Stat Blue, Home, look for a 2 proportion test. One sample there, one sample confidence, one sample size, confidence interval. Confidence interval comparing 2 proportions. Confidence interval comparing 2 proportions is like almost exactly in the middle of the page. If you click on that, it's relatively simple. You are asked to supply N1 and P hat 1. Asked you to supply N2 and P hat 2. So N1 was 628. N2 is 2309. P hat 1 is 0.07. You can just enter it as a decimal. P hat 2 is given as 0.11. Just remembering that in the proportions, you're entering those numbers as decimals, not as percents. 2309, 628. Underneath it, it asks you confidence level. Well, we're doing a hypothesis test for 2 proportions. I did the same thing again. I selected the one for confidence interval. 628, 2309, 0.07, 0.11. As I entered in there, I'm testing for not equal to, and I calculate. And it tells me my p-value is 0.0032. Based off of a z-score that came from this equation, p1. So for me, that's p young minus p hat old minus 0. It's 0 because you have the null hypothesis. If they're the same, then they're 0. Denominator is p hat 1 q hat 1, so that's y, over n1 plus p hat 2 q hat 2 over n2. And it tells me in Stat Blue that z-score is negative 2.94. So again, p-value, 0.0032, very, 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 very small. I'm going to reject the null, like very easily. I'm rejecting the null, accept the alternative. There is significant evidence to show that there is a difference between the age groups for those who use e-readers. Make sure if you're doing a hypothesis test that's not equal to, that in the end you don't say it's less than or greater than. Is it less than? Yes. Significantly less than? Yes. but we're only testing to see, is there a difference? So I cannot make a more precise answer than what the question is asking. My next slide? No, I don't. Here we have, in reading, take a moment and read that. Individuals drive, customers. Whether or not they're independent. We only have one test in our arsenal for independence. It is the chi-squared test for independence. And that happens on Stat Blue. So in Stat Blue, you would have gone to the chi-squared two-way test. Had to add a couple columns. Boom, boom, boom. Sub, mid, full, van, truck. Then the ages, or family size, right? 1, 2, 3 to 4, and 5. Enter these numbers. That probably takes the majority of your time. And when you do that, it gives you this printout. So it's chi-squared. I said it's chi-squared because that's the only thing I have. For goodness of fit, that's what a chi-squared looks like. And my chi-squared value is right here. It's 15.8284. Came from this little nugget right there. P-value, area in that tail, 0.0706. Greater than 0.05. I cannot reject the null. There is not enough evidence. There is not enough evidence to reject the claim that family size and vehicle purchase are independent of one another. The differences we see are probably just due to chance. Notice I did not say they are independent. There's just not enough evidence to suggest that they aren't independent, because the hypothesis for a chi-squared is that not, it's words, not symbols. Vehicle type and family size are independent. For the alternative hypothesis in a chi-squared, we would say vehicle type and family size are not independent. Just like when we do hypothesis tests for not equal to, this is just not whatever that is. If we say this is something, then this is the not thing. So they're not independent. So there's not enough evidence. There is not enough evidence to suggest that vehicle type is independent of family size. It means they might be independent, but there's not enough evidence to say it's not independent. Another example. Probably going to be a different type, since I'm trying to have like one of each type in here so you can see how they're all worked out. Plant manager concerned her equipment may need recalibrating. It seems that an actual weight of 15 ounces cereal boxes it fills has been fluctuating. The standard deviation should be at most 0.5 ounces. In order to determine if the machine needs to be recalibrated, 84 randomly selected, okay, that's going to be N, for the next day's production are weighed. The standard deviation of those 84 boxes was 0.54. Does the machine need recalibrating? So we're testing to see, is the variance equal to 0.5. It says the standard deviation can be at most 0.5. So that means if it's out of whack, the variance is over 0.5. So a test for variance, the only test we have is the chi-squared test for variance. It'll be like this. I got a lot of degrees of freedom, so it's going to look almost like a normal curve. Chi-squared. So again, for conditions, I would say I am testing for variance, and it's one sample. The only thing I have for a one sample variance test is chi-squared. Chi-squared test for variance. All right. I write down my null hypothesis, recalling again that variance is sigma squared, and it's supposed to be 0.5. Well, at most 0.5. So it can be anything up to 0.5. We tested and got 0.54. Is that too much to be considered greater than 0.5? That's what we're going to test and find out. Using that formula, that's the chi-squared formula for a one sample variance test. So n minus 1, that'll be 83 times s squared. S was 0.54 squared divided by 0.5 squared. We need to find that number. 0.54 squared times 83 divided by 0.5 squared. My chi-squared value is it that high? 96.8? That seems awfully huge. 83 times 0.54 squared divided by 0.5. Oh, yeah, it will be. Yep. 96.8. That is huge. But for 83 degrees of freedom right there, I'd put 96.8, which is not my next slide. And that number, so we'd be getting that. So the one sample variance test using chi-squared is not on StatBlue. So we'd have to use applets for chi-squared, chi-SQ, variance, degrees of freedom 83. This number was 96.8. And my guess is essentially, oh no, it's much bigger than I thought. Oh, wow. There we go. Here is 96.8. This area is 0.14276. That's what came in this little red box there then. And then I'm hoping in your heads you're instinctively going, I do not reject the null. There was a 14.27% chance that we could have got results like this randomly. That's not uncommon, which means there's not enough evidence to suggest that the standard deviation of weights of cereal boxes is over 0.5. We would expect weights to fluctuate, and this was not out of the ordinary. What if we sampled on 2 different days? Well, now we're doing a 2-sample variance test. Oh, my pen. Hold on. Now we're doing a 2-sample variance test. My null hypothesis will be that, not mu, variance of the first day equals the variance of the second day. My alternative hypothesis will be, is there evidence that the variation in cereal boxes is decreasing? That day 1 is over day 2. And a 2-sample variance test is a one-way ANOVA, it's a F test. All right. And the formula for the F test was, once we did reducing, whatever you listed as your first standard deviation divided by the second one squared. So this would be, first day was 0.60, second one was 0.51. And again, here, when we're looking at the F test, we're finding out if they're the same, we would expect them, when divided, to equal 1. The further away we get from 1, depending on degrees of freedom, will be what we do. So it's an F test, and down here, we have the 2 degrees of freedoms that we have to figure out. The first sample had 71, so this number is 70. The second day, oh, I'm sorry, no. The first day was 50, which means this number is 49. Just like degrees of freedom, it's n minus 1. The second formula, or the second sample was 71, so this would be 70. In the applets page, again, because StatBlue does not have the F test, so I've been corrected, yes, I forgot to square these, which means this is now 1.384. And if I change that, 1.384. Now my area is, so I go to the F distribution, 49 and 70, I entered there for the 2 degrees of freedom, right? Because it was 50 minus 1 and 71 minus 1. The X value that I got was 1.76. 1.176. And go to my calculator. Applets. Oh, need to go F test EF. It's just f.html. 49, 70, 1.176. That area is 0.26403. Do not reject the null. Cannot accept the alternative. Even though the variance is, the second one was less than the first one, that difference could have just been due to chance, because it could have happened 26.4% of the time. And that's not unusual. There is no reason to believe that the variance is decreasing. .10608. So I would still not reject the null. But that's a good, probably, way to prep for this exam. If you did the same thing that I just did, forgot to square, but you wrote the equation down, but then you didn't execute it the right way, you can still get a full 4. Essentially correct, because you understand the process. You had a good, hopefully a good conclusion. Do not reject the null, cannot accept the alternative, because it's not, because 0.10 is not less than 0.05. And then you would say, because this only happens 10.6% of the time by chance, there's not enough reason to believe that the variances are going down. The differences we saw were probably just due to chance. Good. So once you come into the room for the exam, it'll be all sitting out, and you can just start right away. So if you also happen to get here a couple minutes early because you're afraid that 2 hours isn't enough time, that's fine. And then I'll give you, I got one other nugget of instruction to give you on exam day, but I'll wait till exam day because right now it doesn't matter. So it doesn't impact anything in terms of prep. All right, we'll see ya.